So, as some of you noticed, I put on the board that you have a quiz that is due tomorrow. That should be quiz 5, if I have numbered things appropriately. So this is on Canvas. And the quiz code for it, you should write this down because you'll need it, is capital Q 5, because it's quiz 5, and 11222. So that'll get you in. You will have half an hour. If you are somebody who should have extended time, check with me to make sure that I have your letter of accommodation so that I can give you that extended time. I've taken care of that for a couple of people, but if you're not sure, just shoot me an email and I will check into it. Let's see. Okay. We need to get into chapter 13. Your lab this week is about chapter 13, so you've got to work on that. But vocabulary for chapter 13 will be due Sunday night. We do not have class on Friday. Sorry, I'm looking for things at the same time I'm talking. That's not conducive for clarity of speech. Okay, so no class Friday. But vocabulary 13 due Sunday, and then I decided to give you all an extra day to do your exam reflections. Okay, so first I want you to pull out the packet that is the activation, energy, and catalysis. So you did most of this in class. Now remember, when you see delta G, that's our Gibbs free energy, and that's mostly made up of delta H. So sometimes we use those terms interchangeably. So you can think of delta G and delta H as the same thing. They both tell us endothermic and exothermic. So don't let that throw you. Just pretend it's an H and you'll be good. And then I told you did not need to do questions 6 and 7. Question 5 was one I had put on the board. I'm not really going to be looking at that, but I derived that for you on the board. In a little bit, we're going to be looking at this graph on page 253. So take a second to look at that. So this is a place where people commonly get it confused with another graph. So I want to make sure that you know there are 2 different graphs and you have to look for the differences. So when we talked about the order of the reaction based on what the graph looks like, for the first order, we had natural log of the concentration, right? Now, if we look at this graph, it does have a natural log, but it's natural log of K, not natural log of the concentration. So this is a different graph, all right? The x-axis, when we were looking at a first order, was time. So we were seeing how the reaction was progressing. This is 1 over capital T. So that capital T is our temperature. In what units? Kelvin. So some people were having trouble with some calculations in the homework. Part of the problem people usually have is make sure it is in Kelvin. Okay, so different things on the axis, and we're going to find that it tells us some different information. So this is kind of the basic form here, natural log K2 over K1. I also have it written over here for those of you that are too far away to see that side of the paper. All right, so there on the chalkboard with my window, Riley, you can see this is the form of the equation. So this is the y-axis here, natural logs of k's, and this is the x-axis. So one form of our linear equation that we often talk about is y equals mx plus b. But when you were in algebra, you probably also talked about the point slope form. And you can have y2 minus y1 is equal to m times x2 minus x1. So this is just a different form of a linear equation, okay? If you don't remember that, just trust me, it's just a different form. So this side here is our y-axis. That's what's on the y of the graph. And this is the x right here. So what does that make what I have in the box here? The negative EA over R. What is that? That's the slope. Now, when we were looking at our graphs that told us what order it was, we could just look really easily and find the rate constant because the slope was either the rate constant or the negative of the rate constant. But in this case, the information that we're looking for is a little bit more embedded. So we're going to have to do some problem solving. So take a second to take this negative EA over R equal to slope and try to rearrange that to get EA by itself. Remember, EA is your activation energy. How are we going to get that by itself? And using our basic algebra tools. Rearranging equations is something that's real key to chemistry and other sciences. So it's important that this not freeze you up and make you panic so much you can't move on. Okay, you know how to do basic rearranging of equations. All right, anybody think they know what EA is? What's that equal to? I heard a noise. I didn't see where it came from. Julian, what do you think?
I mean, I know what EA stands for, but I don't know what the actual number is.
Okay. Well, it's going to be slope times something. We're not going to move slope. That's on the other side. What? Okay, yeah, we got to multiply by R because in order to get this R out of here, we're going to multiply both sides by R. Okay. Oops, put that in parentheses. What else? What am I going to do with that negative? What do you think?
I was going to say divide by
Well, we're just looking at rearranging this right here to get EA by itself. So we're really close, but we got a negative sign we got to deal with. We can divide by -1. We can multiply by -1. Whatever we do, we're going to end up with that negative over there. Okay. So when I look at the graph and have the equation on the graph and it gives me a number for the slope, it says 2205 or something like that. I can say, okay, that's this number, the 2205 or -2205. The negative will cancel the negative in the slope. And then R. Well, R is a constant, 8.314. I will always give that to you. R is in joules. Okay. So in lab, you probably got something that was in the tens of thousands of joules, and then you changed it to kilojoules because just having numbers in the tens of thousands is just too big. We like numbers between 1 and 100. So looking at the graph here, what is the difference between the curve for the catalyzed reaction and for the uncatalyzed reaction? Okay, the catalyzed reaction takes less energy. So they're the same starting point, the same ending point, which means that if we find delta H, the enthalpy of the reaction, we're going to find the same delta H for both of them because that just looks at the starting and the ending. So the difference is just how high that activation energy goes. And that's kind of an important concept for when we get into the steps of mechanisms, but let's remind ourselves, what does a catalyst do to a reaction? It speeds it up, right? So the lower the activation energy, the faster this is going to go. Okay. So that's going to be kind of key for for interpreting the different mechanism graphs. Hopefully you took a look at that on Canvas, the different, let me close this off here, the different possible mechanisms or the different curves and whatnot. So if I have a tall hill, that's going to be a slower step. If I have a shorter hill, that's going to be a faster step. And if I have two that are going from the same beginning and ending points, the one that is lower is probably catalyzed. So the first page was mostly review of things that we had talked about before. So I'm not really going to spend much time on those, but then we get to model 2 and there's just a lot there. So some of the key points here is that when we talk about a mechanism, what we're saying is, how are the molecules physically coming together in order to make this reaction happen? And that generally happens in steps. So when I have a step, or what they call an elementary reaction, so an elementary step or an elementary reaction, what I see for the reactants are the actual molecules coming together. And we can describe how many are coming together with the molecularity, right? So if I have one molecule, it's unimolecular. Okay, now both of the steps in model 2 there have 2 reactants. Okay, now it looks like step 1 only has 1, but there's actually 2 molecules there because it says 2NO. So 2 of those are coming together. It's not just one that's like spontaneously bursting or running into a wall or something. There's 2 of them bumping into each other. So we call that bimolecular. Just like a bicycle has 2 wheels, this is bimolecular. And those are the most common types of reactions. Either it just runs into anything at all and it reacts, or it runs into something specific and it reacts. Now we can have termolecular, which would be 3. But if we think about what that means that I would have to have 3 things all hitting each other at the same time and all facing the right way. So if we think about car accidents, it's a lot more likely that just 2 cars are going to run into each other than it is for 3 cars all at the same time to run into each other. Okay, so it's possible, just not very likely. Okay, so far we have mechanisms have steps. The steps are elementary reactions, and we can count the molecularity by how many reactants there are. But usually elementary steps only have 1 or 2 reactants. Okay, so if you look at the arrows in steps 1 and 2, what's the difference between the arrows? Still looking at model 2 here. Thank you, Sarah. Yeah, step 1 has arrows going in both directions, which means that at the same time, both reactions are happening. So this is back to that concept of equilibrium, just like when we talked about solutions, where some of the crystals are dissolving, but at the same time, some of the dissolved particles are getting together and crystallizing. That's happening at the same time. You sort of establish an equilibrium with your laundry. You're constantly wearing clothes, so they're constantly getting dirty, but then you wash them. So we have both processes kind of over an extended time happening at the same time. And when they happen at the same rate, we produce an equilibrium. So if you like wore your clothes and washed your clothes every day, you wore one outfit and washed one outfit every day, then you would have an equilibrium. Okay. So usually when you see equilibrium, it's labeled as fast equilibrium. And so we're not too concerned about that. The second one is labeled as a slow reaction. Now, the slow reaction is also what? What does it do about the overall mechanism? What does it tell us? So this is something that was in the video, but if you read down below where it describes step 1 and 2 and below where it has equation 1, what does that sentence say? It is the rate limiting step. So if you think about all the different steps to doing a process and you want to speed up that process, you want to speed up the slowest step. So if doing your homework requires finding a pencil, sharpening a pencil, which takes you, a minute altogether, and then sitting down for 2 hours to study, finding and sharpening your pencil faster isn't really going to speed up the reaction, right? Finding a faster way to study is going to speed up the reaction. So when we look at these multiple step reactions, and they're usually only 2 or 3 steps, we're going to look for which step is the slowest step. Now, the packet always deals with the second step as being slowest. I'm not going to give you anything that complicated. We're going to have reactions where the first step is the slowest. And so we're just looking at that reaction. But this one, for those of you that are interested in more advanced careers and things like that, the kind of critical thinking that goes into sorting out what would be the mechanism if the second step is slow is a helpful thing. But let's take a look at what we have here. Let's see. We have 2 elementary reactions. We talked about the molecularity. How is the rate law determined? So we spent a lot of time at the beginning of this chapter talking about how we get those exponents from the rate law from doing an experiment, not from the reaction itself. And that's because most reactions have multiple steps to them, so we don't know where they're coming from. But if I know that I'm just looking at the actual molecules that are coming together, if it is an elementary reaction, then I can get the rate law from that step. So let's go back to, it asks about the rate for step 2 and the reverse reaction for step 1. So if I'm looking at step 2, and I'm going to stop sharing for a minute so that people at home can see the chalkboard. If I'm looking at step 2, the actual reaction is N2O2 plus O2. And then I just have a forward arrow. It's not equilibrium. And I'm getting 2 NO2. This is the elementary reaction, and this is saying I actually have a molecule of dinitrogen dioxide and a molecule of oxygen actually running into each other. When I have an elementary step, and I know it's an elementary step, I take my general formula for the rate law. Rate is equal to K times some concentrations. I'm always going to have K. Now it's labeled K2 in your packet because it's the second step, but it's just a K. And then I use each of the reactions. So N2O2 times O2. Now, your rate law doesn't have any addition in it. It's all multiplication, okay? But these concentrations come directly from the reactants. Does that make sense? I'm not seeing yeses, I'm not seeing no's. Give me a second to process that. All right, now if we look at step 1, it's asking us about the reverse of step 1, okay? The reverse of step 1, I'm going to actually switch the reaction around to reverse it. If I turn that reaction around, it's N2O2 gives me 2NO. Okay. So the rate law will be rate is equal to, it's the first thing I always put for a rate law. okay? And they label that as K-1 because it's the reverse of step 1, but it doesn't matter how we label it, it's just a K. And then what's gonna go here? Gonna be something in brackets, some concentration, which chemical? It's gonna come from this reaction. So this is step 1. I'm gonna label it as reversed, right? So I'm just gonna take whatever the reactant is here, the N2O2. Let me. I'm looking at step 1 in model 2. Okay, yeah. All right, so then later on it says, well, what if instead of this happening in 2 steps, what if it all just happens in 1 step? So if you look at question 10, it says, let's propose this mechanism where we just have these 3 molecules all coming together. Okay, so that's where we have 2NO plus O2 gives us 2NO2. Okay, so this is a what if. Okay. So the first part of this is how would we write the rate law? So we said rate is equal to, and what's the first thing that goes after the equal sign? Okay. All right. And then we're going to take what? NO. That's going to go in brackets. Are we done? Now, because we're going to use all of the reactants, okay? But if I have this NO here and there's 2 of them, this is really like saying NO plus NO plus O2, right? So I have 2 of them. And if I'm multiplying each of the reactants, then I should have a square here. Okay? So I have NO concentration times NO concentration times the O2 concentration. All right, so this is what it would be if it were all in 1 step. Okay, and so that's a possible mechanism. And then the other one that they had in model 2 is also a possible mechanism. So they're just kind of comparing the 2 of them and saying, okay, well, we know that in order for it to be a good mechanism, the total mechanism has to match what happens in the chemicals, which it does, and the rate law has to match. So is this the same rate law that you get at the in model 1? Yeah, when you went through the data, this should have been the rate law that you came up with. Okay. But the last step is what's plausible, what's likely. And what did we say about the molecularity? What are the 2 most likely molecularities? 1 and 2, unimolecular and bimolecular. What's the molecularity of this? 3, it's termolecular. So is it possible? Yes. Is it likely? No. All right. Okay, so if you did not manage to do the exercises 1 and 2, if you found that too difficult, that's okay. I mostly wanted you to get through the key questions. Are there any other questions about this packet? This is interesting. You guys get polka dots, but on my computer here, there are no polka dots. I wonder why there's a difference. Okay. So one of the things in the first packet that you looked at, and one of the things that you looked at last week in lab, was activation energy versus temperature. Okay. Now, this is a little bit complex, but it's usually no more than about 3 points on any exam or quiz. So don't stress over it too much. One of the things that people confuse about this is that we have a natural log over here. And so they start thinking, oh, this is the first order reaction. So you got to look carefully at what's on your axes. So the vertical axis is natural log, not of concentration, but of K. Okay. So when I'm doing natural log of concentration, yes, this is when I'm looking at a first order reaction. But when I'm doing natural log of K, if I notice down here, it has 1 over T, 1 over temperature. That's where I'm looking at the activation energy. So this is a graph that is showing me the various activation or the various rate constants at different temperatures. And looking at this data, this might be the data that I took from last year's Crystal Violet lab. I might have just taken the different data points and plotted them. And so we have an equation here, and we have X at the very end. So instead of mx plus b, it's written as b minus mx, okay? So first thing to notice is that our slope is the second number, not the first number, okay? But that slope is going to tell us something. So what is it going to tell us? And so this question is going to ask us how to get there, but I want to take just a second to think about the equation that we have. I thought I had that equation in there, the Arrhenius equation, which is, and I'll write this over on the other side for those of you over there. ln of K2 over K1 is equal to negative EA over R 1 over T2 minus 1 over T1. So you'll notice in this equation that I've written on here, on one side of the equation, I have natural log of some K's, and that was my y-axis. I'm going to put a y under here. And then over here on the right-hand side, I have in parentheses some 1 over T's, 1 over temperatures. So this side is my x. So what does this make negative EA over R? What's that going to work out to be? Slope. Exactly, that's my slope, okay? So when we were looking at the order of the reactions, we could just look at that number and know what K was. But in this one, we have to do a little bit of math, okay? So now let's look at our slide here. First order reaction is carried out at several different temperatures. The data is plotted. How is the slope related to EA? Okay, so if I want to say negative EA over R, remember EA is our activation energy, is equal to the slope. And now I want to solve for EA. I want to get EA by itself. What is the other side of that going to look like? Right. How many of you think this is A, B, C, D? Okay, handful of people, most of you, okay, you can't be this cautious about your algebra. You know how to rearrange an equation. It helped that we worked on this at the beginning of class here, that yes, this is how it rearranges. Okay, so you can memorize that. When you have a test, you can put it on a note card, but you also can just rearrange it. You have the skills to rearrange it, trust in yourself. Okay, we're not going to plug that in though. I had given you on Canvas some practice with different kinds of graphs like this with lots of questions that I might ask about it. And on your quiz, there's several questions related to those types of questions. So looking at this, how many steps is this reaction? Okay, Maddie says it's 3. How did you come up with that?
There's three peaks.
Yeah, 3 peaks or 3 hills that we're going over. So each of these peaks represents one step in the reaction. Okay. So in this reaction, each of those steps has its own activation energy. Okay. Which of the steps has the highest activation energy?
Hmm.
All right, so I heard a couple of people say B. Raise your hand if you agree with that. Yeah, okay, so how did you get there? What about B tells you that it's the highest activation energy? Lauren, what did you do to come up with that? It's the highest peak. Now, we have to be careful because we would get the same answer on this graph regardless of how we did it, whether we did it right or wrong. But remember that we're looking at the difference between the valley below it and the top. We're not going from the bottom of the graph to the top, but the valley below it. So if I look at this one going from here to here, it is less. But let's say that C instead went up like this. So it's nearly as high as B was, but it's starting out lower. This would have been a higher activation energy, even though C would have been a little bit lower. So remember that the activation energy is determined from the reactant right before that hill peak. Okay. So on a graph like this, if we have chemicals labeled, obviously we label the products at the end and the reactants at the beginning. Where would we put the intermediates? Are they going to be A, B, and C, the higher letters, or are they going to be D and E, the lower letters? D and E. So the intermediates are down here. Intermediates are either real molecules that you can have in a bottle and whatnot, or they're at least a little bit stable. They have actual bonds to them and whatnot. And so all of these, water, hydrogen, these are all real molecules, okay? And they are found in the valleys between. What do we call the things that are at A, B, and C? Transition states. Now, transition states are sort of halfway in between metamorphosis. Okay, it's like a butterfly that's like it's in its cocoon, that's a half caterpillar, half butterfly. So we're starting to break some bonds, we're starting to form some bonds, and we don't really have bottles of those intermediate species. Okay, those are transition states. They're short-lived. We can't isolate them. We can't say, there it is, that's what it looks like. So in some ways, they're kind of theoretical as well. All right, and then we can also look at the overall energy of this reaction. So is this an endothermic or an exothermic reaction? All right, Madison thinks it's exothermic. How many people agree with Madison? Yeah, she's pretty smart. It's exothermic. So we have higher reactants than products. So it's a downhill overall reaction. If I had numbers to plug in, then products minus reactants would give me a negative number. So this is an exothermic reaction. And it wouldn't matter whether this was energy in terms of H or energy in terms of G, it would still be exothermic. Okay. Let's say I have this reaction. This is very simplistically drawn. And I have an enthalpy of reaction of negative 85 kilojoules per mole. Remember, enthalpy, the TH, enthalpy is delta H. So TH gives me delta H. The activation energy is, or they call it activation enthalpy, is 120 kilojoules per mole. And it's asking for the reverse reaction. Instead of going this way, when we go this way, what's the activation energy? All right, so what am I going to do with the, well, first of all, what does this line represent? Is that activation energy or enthalpy change? This is the activation energy, so this is the enthalpy change. And since we start higher and go lower, this is the negative, so negative 85, and this is 1 point. So in order to get the reverse activation energy, starting from here to the top of this hill, what am I going to do with those numbers? Basically add them, but remember, since it's a negative 85, it's going to be, you know, make it add a positive. So we'll have the 120 plus 85 will give me the 205. That's how we get that answer. Okay. Questions on this one? All right. When a catalyst is added to a system, say it's this system, and this is weirdly worded. This comes from one of the ACS exams, but it says which dimension is changed. So what they mean is, like, is the value of 1 going to change? Is the value of 3 going to change? Is the value of 2 going to change? So before we answer 1, 2, or 3, what about the graph is going to change? The height of the hill. So this, if we add a catalyst, will come down just a little bit. Will the starting or ending point have to change? No. So if this comes down, will that affect 1? Yeah. Will it affect 3? Yeah. Will it affect 2? No. So 1 and 3 only. Okay, so we talked a little bit about mechanisms today. We've got a 2-step mechanism here. This is more like what I would propose for you. So first of all, what is the rate limiting or rate determining step for this reaction? Step 1 or step 2? And how did you get that? Slow step. So slow step is rate determinant. Okay. So then this says, what is the rate law? So my rate law is going to be rate is equal to, and what do I put right after the equal sign? K, gotta have K in there. So rate is equal to K. And then since the slow step is the rate determining step, the rate for the whole thing is just determined by whatever the rate of the first step is. And so what am I going to put in these brackets here? The reactant. So that's C3H7I. And is that it, or do I need a exponent? That's it. So this is the overall rate law. And then it asks, what are the intermediates, or if there's only one, what is it? So the cation, right, the C3H7 plus, everybody agree on that one? What about I? Is that an intermediate? No, because it doesn't get canceled out. It doesn't get used up in the next step. What about the chlorine? It's used up. It's just an overall reactant because it's never produced later on. We're going to have to find some source of chlorine to put it in there, chloride to put it in. Okay, here we got another mechanism. Rate determining step is the first one because it's the slow one. All right, and this one's written a little bit odd, but notice both of the reactants are the same reactant, NO2 and NO2. It's really just NO2. Okay. All right. And so we want to know, is this a good mechanism? So we have to check 3 things. So first of all, if I add together these, does that match the overall reactions? The overall reaction is what's written at the top. Now I notice that there's only 1 NO2 at the top over here, and I have 2. So that might make me think, that's not going to work. But one of my products is also NO2. So that's going to cancel out. Okay, so what about the other things? Does it match? Yeah, so I've got an NO3 here that doesn't appear in the overall, but it's also on the other side. So those would cancel. So what do I call NO3? What kind of chemical is that? Intermediate. Okay, so it matches. That's our first thing. And then we want to know what's the molecularity of the step. So what's the molecularity of the first step? Bimolecular, it has 2 chemicals. What about the second step? Bimolecular. Okay. Are those reasonable? Yeah, so it's not termolecular, so that's okay. We already talked about the rate determining step. And then we want to know, does it match the rate law? So if I wrote the rate law for the first step as rate is equal to K times NO2, I would square it because there are two of them. Does that match that rate law? Yeah. Okay, so it matches the rate law, matches the overall reaction, no term molecular steps. So this is realistic. All right, and yeah, that's just another one. So stop there because I want to talk just briefly about equilibrium. So in lab this week, you're going to be talking about Le Chatelier's principle. And Le Chatelier's principle has to do with equilibrium. So remember, for equilibrium, we're going to have these arrows facing in opposite directions. So that means both forward and backward are happening at the same time, and they're happening at the same rate. So when we've reached equilibrium, they happen at the same rate. And so we can have an equilibrium constant that tells us, okay, well, when they're happening at the same rate, do I end up with lots and lots of products or lots and lots of reactants or about the same? So when I end up doing my laundry all at the same time, forward and backward, do I have a big pile of dirty clothes or do I have mostly clean clothes? That's kind of what it's telling us. And so the equilibrium constant is also a K because chemistry is confusing. This is a capital K. All right. Rate constant is a lowercase k. This is a capital K. And we find this as products divided by reactants. And most of the time, 99% of the time, it's by concentration. We'll talk on Wednesday about how you can also do it with pressures, but concentrations here. And so if I were going to do this reaction, I would take the product, NO, and because there is a coefficient of 2, I would square it, and I would divide by N2O2. Okay, so that's the first thing. That's the what we call the expression. There's no real numbers to it. I don't know what that calculates out to be. So it's the expression. If I were going to calculate the number, that would be the value. So let's just, in order to be able to work with this a little bit, assume the value turned out to be the number 2. That I have, plug in all my numbers, and this over this is equal to 2. Le Chatelier's principle says, let's say I disturb this system. How can I get back to equilibrium? We're always going to try and get back to equilibrium. How is that going to happen? So let's say I dump a whole bunch of this in. So this number becomes bigger. What happens to what I had calculated for K? K had been 2. When I add more here, is that going to be greater than 2, less than 2, or still 2? Greater than 2. So it's going to be too big. So in order to make it smaller, to get back to equilibrium, I'm going to have to move away from what I just added. So I'm going to reverse the reaction. So we talked about the reaction shifting. We say it shifts towards the reactants, or it shifts to the left. I'm a little bit dyslexic, so saying it shifts left or right to me is a little bit rough. So I try to stick with reactants versus products. Shifts towards the reactants. Typically, whatever you add, it's going to shift away from. So let's say I added instead, I'm back at equilibrium. This is still equal to 2. Now I add N2O2. So I've got more on the bottom. What does that do to the overall value? It gets smaller. So in order to get back to 2, in order to get back to equilibrium, I need to get rid of some of this and make more of this. I need to get this here to be bigger. So I'm going to shift away from what I just added towards the products. Okay. Now the opposite works as you would imagine. If I take something away, and in your lab, you're going to do 2 of these reactions, and in each case, you're going to add something that's going to take away either a reactant or a product. So I might do this by precipitating something out. Okay, so I'm going to precipitate out something. Let's say I precipitated this out. Now there's less of this. If there's less of this number is smaller, overall is bigger, so I need to make more of this. So I'm going to shift towards what I took away. Okay, so Le Chatelier's principle says, if I disturb equilibrium, I'm going to shift away from what I added towards what I took away. Okay. There's another little thing involving heat that we don't really have time to get into, so ask Dr. Fraley or Dr. Demchimino tomorrow if, no, it's Dr. Nunez tomorrow, about what happens with heat. Wednesday, we'll go into more detail, so those of you that have lab later in the week will have a little bit of an advantage.